The strength-to-weight ratio is a critical metric in engineering and construction, providing insight into how materials perform under various loads, while maintaining a lightweight profile. This analysis focuses on 4 common building materials: wood, specifically cross-laminated timber made with spruce pine fir, brick, clay, concrete in the category C25 to C30, and steel ASTM A36. By examining their compressive strengths, tensile strength yields, bending strength, and overall strength-to-weight ratios, we can better understand their suitability for different applications. The following table presents the key properties of each material, including density, specific gravity, compressive strength, tensile strength yield, and bending strength. These properties are essential for understanding how each material behaves under different loads and conditions. Specific gravity, a dimensionless quantity, represents the ratio of a material's density to the density of water at a given temperature, typically 4 degrees, where the density of water is 1000 kilograms per cubic meter. It indicates whether a material will sink or float in water and provides a relative measure of density. For the calculation of the strength-to-weight ratios, the strength value will be divided by the specific gravity. So now, let's go through this table together and fill it in. The compressive strength-to-weight ratio is a critical metric for evaluating how well a material can handle compressive forces relative to its weight, which is especially important in construction where the balance between strength and material efficiency matters. Wood emerges as the clear leader in this category, with a compressive strength-to-weight ratio of 47.45. Despite having a compressive strength of 21 newtons per square millimeter, which is modest compared to other materials, its low density of 442.53 kilograms per cubic meter allows it to excel in terms of efficiency. This makes wood highly suitable for lightweight structures where compressive strength is needed without adding excessive weight. Steel follows with a compressive strength of 152 newtons per square millimeter and a strength-to-weight ratio of 19.49. While steel's much higher compressive strength makes it ideal for heavy-duty applications such as high-rise buildings or bridges, its higher density of 7,800 kilograms per cubic meter means it's less efficient in weight-sensitive designs compared to wood. On the lower hand, brick and concrete show moderate results. Brick has a compressive strength of 16.60 newtons per square millimeter and a strength-to-weight ratio of 11.16, while concrete has a higher compressive strength of 25 newtons per square millimeter but a strength-to-weight ratio of 10.42. Despite concrete's stronger compressive strength, its higher density of 2,400 kilograms per cubic meter makes it less efficient than wood or steel. Brick has the lowest efficiency due to both its moderate compressive strength and relatively high density of 1,487 kilograms per cubic meter. These results emphasize that wood, with its lightness and strong performance in compressive strength relative to its weight, is a superior choice for lightweight, load-bearing structures. In terms of tensile strength yield, which is the maximum stress a material can withstand without permanent deformation, steel is the dominant material, with an impressive tensile strength of 250 newtons per square millimeter and a tensile yield-to-weight ratio of 32.05. This extreme tensile strength makes steel the material of choice for tension-heavy applications, such as cables, bridges, and other structures that are subjected to high tensile forces. Wood, with a tensile strength of 14.50 newtons per square millimeter and a tensile yield ratio of 32.77, comes very close to steel in terms of tensile strength relative to its weight. Its relatively low tensile strength in absolute terms doesn't detract from its overall utility, as the material remains light and efficient for a variety of tension-based uses, like trusses or beams in buildings. On the other hand, concrete and brick perform poorly in this area. Concrete has a tensile strength of just 2.50 newtons per square millimeter, which results in a tensile strength to weight ratio of 1.04. Similarly, brick has a tensile strength of 0.55 newtons per square millimeter, yielding a very low tensile strength to weight ratio of 0.37. These low ratios indicate that these materials are not suited to withstand tension on their own, and typically require reinforcement with materials like steel when used in tension-heavy scenarios. This makes wood and steel far more efficient and suitable for structural applications where tensile strength is required. When considering the bending strength-to-weight ratio, which is the ability of a material to resist bending forces while maintaining a lightweight profile, is of great importance, particularly in beams, floors, and other structures subjected to flexural loads. Wood leads again, with a bending strength-to-weight ratio of 54.23, driven by its bending strength of 24 newtons per square millimeter and low density of 442.53 kilograms per cubic meter. This makes wood particularly suited for applications where both strength and reduced weight are crucial, such as flooring systems, roofing, and bridge beams. Steel also performs well in this category, with a bending strength of 151.68 newtons per square millimeter and a ratio of 19.45. Despite its high bending strength, steel's density of 7,800 kilograms per cubic meter results in a lower bending strength-to-weight ratio compared to wood. Brick and concrete, with bending strengths of 3.20 and 3.50 newtons per square millimeter respectively, have much lower ratios of 2.15 and 1.46. This underscores their limited capacity to resist bending forces, and while they are reliable in compressive situations, they require reinforcement in bending heavy applications. Finally, when consolidating all these metrics into the average strength-to-weight ratios, wood stands out with an average ratio of 44.82, reflecting its superior performance across compressive, tensile, and bending strength categories while maintaining a lightweight profile. This balance makes wood the most efficient material overall, ideal for a variety of construction applications that prioritize strength and reduced weight. Steel follows with an average ratio of 23.66, which showcases its impressive absolute strength in each category, but is offset by its much higher density. Brick and concrete achieve average ratios of 4.56 and 4.31 respectively, showing that while they are valuable for certain construction applications due to aesthetic appeal or cost effectiveness, they are not as efficient in terms of strength relative to their weight. The sources used to create the table shown in this video are listed in the description. Keep in mind that we discussed the materials in the context of buildings, so the properties of CLT made with SPF were used, rather than those of, say, hardwoods, which might be more suitable for furniture or other applications. Here is a version of the overview with some added color, making it easier to quickly identify which materials offer the best strength for each of the forces discussed. This table, along with additional content, is available on the TimberTalk Patreon, linked in the description. If you want to learn more about the world of mass timber, subscribe to this channel.
Stay informed, stay inspired. TimberTalk.